Okay, welcome everybody to the 6th JMD webinar. I'm Mark Fuge, and on behalf of the organizing committee, which includes Danny Silva from Texas A&M University and Fayez Ahmed from the Massachusetts Institute of Technology, would like to welcome you. Today's webinar is going to be focused on artificial intelligence in engineering design. And we've got 4 talks for you today. What I'll do is I'll introduce the talks and the speakers as we're going. And then what we've asked everyone to do in terms of questions is if you do have any questions for the speakers, we'd ask that you'd like to, if you can, save those until the end. The format of today is going to be the 4 talks followed by panel discussion and questions. And then we'll have a Gather.Town networking event where you get to meet with some of the speakers and other participants after the event. Okay, so thank you everybody for joining us today. Okay, for our first speaker, the first speaker today is going to be Dr. Sayan Ghosh from GE Research. And he's going to be presenting a paper. I'm not going to mention all of the authors, but we'll put a link in the chat for anybody interested in finding out about the paper. His paper is going to be entitled Inverse Aerodynamic Design of Gas Turbine Blades Using Probabilistic Machine Learning from the February issue of this past year. Okay. And you can see the link in the chat. Okay, Dr. Ghosh, we're ready for you whenever you are.
Thank you, Mark. Thank you for the intro, and thank you, the organizer, for the invitation. Should be able to see my screen now, or I'm probably doing, hold on. All right, should be able to see my screen. All right, so I'm Sayan Ghosh. I'm senior engineer in probabilistic design and material informatics at GE Research, New York. So the title of the talk today is Inverse Aerodynamic Design of Gas Turbine Blades Using Probabilistic Machine Learning. And this was done as a part of ARPA differentiate program. And we did this work in collaboration with the University of Notre Dame with Professor Nicolas Zavares. So although the paper is mainly focused on the aerodynamic design, today I'm going to show a little bit extension of that, which we never published, but might be interest to the audience. So again, here, what I'm doing, I'm going to talk about the motivation, why we started this project, going through invertible neural network, which is our main tool, and go through the framework which we developed and show the results on aeromechanics design. So a bit of information, most of the folks probably know about it. When we talk about industrial gas turbine, these are the huge gas turbine which can actually eventually can power order of 300,000 houses. And of course, these are complicated designs consisting of thousands of components, subsystems, and so on, and needs hundreds of thousands of design engineers to design those things. Now, a typical design cycle time for these kind of complex system takes around 3 to 10 years, again, depending upon whether you're looking into a derivative design or completely revolutionary design. And then, of course, that means that more and more, you need to spend hundreds of millions of dollars to design these kind of systems. Now, the ARPA differentiate program, what they were looking was coming up with AI machine learning technologies. How can we reduce the design cycle time and push the boundary of getting more and more performance? So that was the whole idea of this project. So if you look back, what's the current design process? We typically start with some target performance metric which we want to achieve, and then we go through these iterations where we are modifying the design and trying to achieve that. So it goes through multiple iterations. And again, the evaluation itself has a lot of challenges like multiple constraints, discipline, stakeholders, and so on. Right. Now, if you just take the last stage blade of these gas turbine, which I'm showing here on the right, and the reason we picked this up was because that plays one of the major, that's one of the major components which plays a role in the overall performance of these kind of gas turbine, particularly the efficiency. So design of these blades itself will take around, order a few months to a year. And then more often than not, what happens is we go through different iterations. And as soon as we get to some feasible solution, the design is locked in because, you have already spent so much time and money on it. So basically what happens is you don't get much time to push these designs towards optimum. So because of these iterations, things get slow. So the idea or ultimate idea is that the designer will come up with some design requirements, performance, and we have this the magic machine learning AI based agent which will basically without going through any iterations, will be spitting out all the possible design solutions which can be able to achieve those targets. And if we can get to that point, then basically, which means that now we are reducing the overall design cycle time, cost, and probably push the boundary of our performance to uncertainty analysis, robust and reliable design, and more, and particularly, it's a new learning curve, because what we typically do is we learn how if you change the design variables and how it impacts the performance. But now what you're doing is you're changing your performance requirement and see how the design evolves. So it's a completely different learning curve, which we can envision with this kind of techniques. So the tool which we use for this project to do the inverse design is called invertible neural network. So the basic fundamental theory behind the invertible neural network is normalizing flow. The idea is of normalizing flow is basically you're mapping complicated distributions, so something like this, to a very simplified distribution like Gaussian distribution. And the way you map that is through series of transformation and which are invertible in nature. The reason you want to do that is basically because if you want to sample from this complicated distribution, I mean, one of the reasons, and of course there are many, if you want to sample from this complicated distribution, what you basically need to do is sample from the simplified Gaussian, let's say Gaussian distribution, and you can go through this transformation and basically get the sample from a complicated distribution. So that's the fundamental theory behind, on which the INNs are built on. Now, there are different ways to do normalizing flow. One approach is called real non-volume preserving algorithm, which is real NVP. And the way in real NVP it happens is basically you're transforming X into a latent space Z. And the latent space, when I'm saying is that's normalized, the simplified distribution. So the way it is done is going through a series of transformation, as I'm showing here on the top right side. So it's an architecture which is built on real NVP. So what you do is, let's say you have a complicated variable X, which has a complicated distribution. So you basically break it down into U1 and U2. So let's say it's a 100-dimensional variable and you break it down into U1 and U2. U1 remains unchanged during the transformation and U2 goes through a scale and shift to becomes V2, and then you concatenate that to become Z. Now, the scale and shift which happens on U2 is actually also a function of U1 as well. So as you see in this connection, right? And what you can do is, the main question is to evaluate the SNT functions. And what we can do is basically represent this SNT using deep neural network and train those neural network so that when you do this transformation, the Z distribution is close to Gaussian. So once you train this ready, all right. So again, this is one single transformation block, but you can have series of these blocks. Now, once you train this network and you want to do an inverse going from Z to X, what you basically do is you re-architect those mapping. Now you can see that V1 from Z to X, you again break down Z into V1 and V2. V1 remains unchanged. V2 goes through descaling and deshifting, and that becomes U2, and then you concatenate becomes X. So no more retraining of the network, it's just re-architecturing the network to just do the inverse mapping. So what you do is you basically train forward, and inverse is basically byproduct of that. So what I talked about so far is INN, which is going from X space to Z space, but in design problem, you have a Y variable, which is the performance. So what we are looking into condition INN, which is probably what we are basically is probability of X given Y, right? So the way you do that is you condition the scale and shift network as a by putting in the Y as an input to the scale and shift network, and that basically helps in conditioning it. So I'm not going to go into detail, but what eventually happens is basically when you want to train this network, you have X design and Y performance, and you try to train this network, the invertible network, or series of these invertible networks, so that the Z distribution is Gaussian. And once it is trained, you want to do an inverse problem. What you do is for a given target Y, you basically sample from a standard Gaussian distribution. If so, Z is defined as standard Gaussian. You sample from it and basically goes in the inverse direction and basically gets the samples of design variables. So that eventually will generate all the solutions for for the design condition on that particular output. With that being said, again, the framework which we basically use called ProML ideas, the idea here is that, again, for these kind of networks, you need a lot of data points. So what we did is that we break it down into two-step process. And the first step, what we did is we build a forward model of the problem we are trying to solve. So it will be a generative model. And what we did is using our in-house DHM2, which is a multi-fidelity Gaussian process based on Kennedy-O'Hagan's framework. And again, in fully Bayesian setting, we did full MCMC using parallel MCMC to train this network. We also did adaptive sampling on multi-fidelity process to reduce the number of data points which we did. Once we have that forward model, which is going from your design variable to your output performance variable, we use that generative model to artificially or generate synthetic data, which was then used to do invertible model. And again, you can do it in loop. So eventually what you're doing is you can generate infinite number of data from the forward model. So the problem which we solved, the paper was most focused on the aerodynamic design of these blades, but I'm showing here a little bit more complex, which we solved recently. So again, this is the last stage blade of the turbine. The way it is defined is basically by 85 dimension input variable. So we break it down, we break down the blade. The way we parameterize it, basically we have 7 sections of the blades, and each section is defined by 12 variables, and then there are a couple of other variables here. So for each of these analysis, we did, aero analysis, structural, then modal analysis, flutter analysis. And again, this chart shows, the complex nature of the problem. From 87 axes, we have multiple disciplines where variables are connected to each other. Those are the coupling variables. The one in the reds are the one which we were looking as a performance requirement, right? So the first step was basically do this multi-fidelity analysis, and I'm showing here like different kind of grids. The fine mesh are the industrial standard grids which we use, and the coarse mesh are basically the one which have error in it but still gives good correlation. So the coarse mesh was almost 4 to 6 times faster, but again they were not cheap enough. So we have to do a multi-fidelity analysis with adaptive sampling, where deciding which fidelity to run while we are doing this. So what we found that with this kind of approach, we were able to build a good multi-fidelity model with over 90% accuracy, with having just 200 to 300 high fidelity data and around 300 to 500 low fidelity data, and save us almost around 35%. So again, 35% is just based on multi-fidelity with adaptive sampling. But if I look at overall around, it was around more than 50% cost saving with the current standard practice. So again, I'm showing here those 4 different disciplines, showing different accuracy, how many data points we use. So if you see here, we are actually using less than 500 data points for both low and high fidelity. So with 87 dimension problem, we were able to achieve almost an accuracy of 90% or higher for all the metrics which we're looking at. Once that is done, the idea was to train invertible neural network. Again, the data was synthetically generated with invertible neural network, and trained. The network was trained. And what you're seeing here are the validation study of that invertible neural network. So the validation is kind of a little different when we are talking about inverse design, because here in this case, your x-axis is the target value. So what you see here is these are the target values which you provided to the network. So here in this case, aero efficiencies, we provided a target. And again, these are normalized values. And the output is basically, so once we have the target, network generate the designs, and we have to run that design through our forward process to see how much it predicts. So Y value is the prediction. So what we ideally want is whatever target we provide, the design generated by the invertible model should be able to perform. So a Y output is the forward model ran on the data or the design generated by the invertible model. So it's a little bit involved here, but ideally what we want it to be on the 45-degree plot. So again, some of these are shown here. We have showing here around 6 of the scalars, and most of them we did pretty good. And again, as I'm saying this, this is not a separate model. It's one single model where the designers provide all the target inputs as one vector, and the outputs are generated like this. So all these are correlated plots, which I'm showing in just 2D on a marginal setting. And again, this is another plot for the pressure profile. So what you see here, the green one is the target pressure profile which we provided. And the blue one is the basically results coming out of INN designs. And the uncertainty is uncertainty associated with our forward process, because again, we are sampling multiple designs and calculating. So with that, I think I'm close to my time limit here, but the main idea here is, with this explicit inverse design, the idea is to reduce the overall design cycle time, and somehow able to push and save the design cost associated with it. What we found that with just the main cost comes from building the forward model, because we still need data to generate models. So we were able to achieve almost 35 to 50% cost saving in the forward model. But once that is done, the invertible model is trained. Every time you use the invertible models, it saves time. So it's basically accumulating over time. So depending upon how many times you're going to use an invertible model, the cost saving goes up linearly. And again, there is no limitation to where these things can be used. And we have different applications in GE where we are trying to get this implemented and tested. With that, I think I'll stop here. And yeah, if there's any question, please reach out to me. And yeah, thank you.
Great. Thank you, Dr. Ghosh. That's great. As a reminder for all of our participants, I have lots of questions, and many of you probably do. We're saving those all the way to the end. If you want, you can also post them in the chat if you'd prefer. Okay, great. So our next speaker is Dr. Christopher McComb. He's a faculty member at Carnegie Mellon's Department of Mechanical Engineering, where he leads the Design Research Collective. He also serves as the director of the Human and AI Design Initiative, which is an interdisciplinary and international group of researchers focused on the application of human AI collaboration to design. And his research interests include human social systems in design and engineering, machine learning for engineering design, and human AI collaboration and teaming in STEM education, with funding from NSF, DARPA, and private corporations. So he'll be presenting his paper entitled Design Strategy Networks, a deep hierarchical framework to represent generative design strategies in complex action spaces. And take it away, Dr. McComb.
All right, thank you very much for the introduction, Mark. I'm very excited to have the opportunity to present this work today. And I'd also like to recognize the fact that this was a collaborative paper led by Ayush Raina, who recently graduated and is now working with Sony Research, and in collaboration with John Kagan at Carnegie Mellon University. And this work was funded by DARPA through the A-Teams or Agile Teams program. So the type of design that we're focusing on in this work is configuration design. And configuration design really amounts to any problem where you are where you have the opportunity to configure or compose a solution based on a set of components. And those components may be parameterized or parameterizable, but really you're constructing a solution based on a set of components. And this can be as trivial as figuring out how to rearrange your living room, but it can also be extremely critical. So this is a picture of the CO2 scrubber that the Apollo 13 astronauts cobbled together from components that were available on board. So this was a canonical case of configuration design for a very mission critical component. So in general, when we're doing COTS design with components off the shelf, we're doing configuration design. And this generalizes to things like planning and scheduling as well. And we know that if we are designing an algorithm to do configuration design, or if we ourselves are doing configuration design, decisions about what, where, and when to make changes, how to iterate on the solution, really drives effectiveness. So this is an example of some steps in the design of a truss structure or a bridge. And we're adding members, moving joints, resizing components, and the order that we do them in matters. What we're doing, what type of action, whether we're adding a member or adding a joint, matters. Where we do that action, where we add the joint, of course, has an impact. And also when we take these actions matters, because that will constrain or open up additional design opportunities within what tends to be a pretty large design space. We're dealing with, a combinatorial explosion when we do configuration design. And we can formally define this decision-making process of choosing what and where and when to take actions as a design strategy, or in ML parlance, a policy. So here we have the policy function, pi, which takes the state of the design solution at time t as an input and yields a probability distribution over possible actions at that time. And when you're doing this, you might not think about a probability distribution over actions, you just choose a single action. But representing that probability explicitly encodes a little more information in this process. And being able to define or learn this function to go from the environment and the state to a recommended action or change is really a key step towards computationally emulating human design behavior as we advance the next generation of design automation. Existing methods in other application domains outside of design use deep neural networks to learn policy functions like this. So this is an example of a network that takes an input from an Atari game, Pong, feeds it through some hidden layers, and then makes a decision about whether to move up, to move down, or to stay in place. And this is a simplified example, but it highlights the fact that most applications tend to deal with fairly simple action spaces, where an action space is this set of possible actions or possible modifications. In design, that's not always the case. We tend to have a much more complex action space. Specifically, there are three attributes that make the action spaces of design typically very complex. So the selection of actions is inherently state dependent. There's not one action that's always good or always bad. That will vary depending on the current state of the solution. Our actions tend to be hybrid in nature. So there's a combination of discrete parameters and continuous parameters, and we have to worry about both of those to select an effective action. And then finally, the action space is temporally divergent. So as we take additional actions, there are increasingly more possible actions for us to take. And this is in contrast to things like games, where there tends to be a convergent space. So the driving question in this research is, can we learn an end-to-end model that encodes design decision-making? That's sort of the broad statement. To state that with a little more, in a little more specificity, we can expand it and ask the question of, can a data-driven learning approach with hierarchical action representations, say what we mean by hierarchical in a second, but can that emulate human decision-making behavior in complex action spaces better than a baseline non-hierarchical method? So really what we're bringing to the table here is a hierarchical approach that makes it easier and makes it a lot more efficient to do these predictions. So to address this, we introduced design strategy networks. And this is, the DSN is a generic framework for representing strategies in design in these complex action spaces. So the exact details of the framework you can find in the paper. I want to draw your attention to a couple of things. So these two red boxes are in some sense the outputs. And then we have three primary components. We have an encoder, which provides features of the design state. We have a spatial action network that handles the where of where I should do an action. And then we have a selection network that handles the what of what action to do. So if I can build a simplified version of this, it might look something like this. And this is where the hierarchical piece comes in. So we take a look at the state of the solution. Then we decide where we should be making a modification. We decide on the spatial region where we should make a change. And then using that as a prior, we decide on the exact type of change that we should make. And it's this hierarchical process that allows us to achieve better predictability. So in addition to that hierarchical process, there are also a few nice characteristics that we built into the DSN framework. This methodology is purely data-driven, and that's in contrast to some other approaches that require a combination of data-driven methodology and some rule-based approach that encodes knowledge about the domain. There's a modular architecture. So we have distinct components. So we actually have 3 separate networks here that all have distinct tasks. So we can iterate and improve those independently. We have a generic action space. So this can handle actions that are fully discrete, fully continuous, or combinations of the two, as we often see in design. And because we're making an explicit prediction about the area where we should make changes, we have a degree of spatial interpretability. So this provides some interpretability for the predictions that we're making. We decided to compare our DSN framework to an imitation network that is non-hierarchical, and this is based on the Atari DeepQ learning network. So if you're not familiar with Atari DQN, essentially what it does is look at the current state of an Atari game, and then based on a neural network, decide what actions to take in that game. And we're not applying this to Atari, but the same network architecture applies in our case. The key difference between the DSN and the Atari DQN is that the DQN is looking at the spatial prediction and the discrete prediction simultaneously at that output layer. So it's non-hierarchical. And we do a comparison between DSN and Atari DQN on the task of predicting human behavior during truss design. So we have a data set of humans designing bridges or truss structures, and we track this over time. We have something like 40 individuals, each of whom took 400 to 500 actions. And they took actions like adding nodes, adding members, increasing thickness. So this is what constitutes our action space. So in doing this comparison, we looked at several different metrics. I'll break these down a little bit later, but we looked at 2 metrics for our spatial distribution and 2 metrics for our action distribution. The more important metrics, and the ones that are a little novel, is spatial accuracy in an n-unit sense. So here we ask and answer the question, how often is the true spatial region within n units of the prediction? And then top K accuracy for the action distribution. So how often is the true action within the top K predicted options? So the next slide, we're going to jump right into results. So this shows the imitation network, the Atari DQN, versus our DSN methodology across these 4 metrics. And for our loss functions, lower is better. And we are much lower for the DSN. And then for accuracy, higher is better. So we're much higher in accuracy. I want to draw your attention to selection accuracy, which is about the final rule that's selected. And the imitation network is at about 50%. And we have a huge action space, so that's much better than chance. But then our DQN actually gets up around 74%. And this is top 1 selection accuracy. We can break this down a little bit further and look at top K selection accuracy and vary the number of units. And essentially what this shows is that regardless of the threshold that we set, whether it's within 0.1 units, within 1 unit, 5 units, or if we're looking at top 1 accuracy, top 3 accuracy, our DSN outperforms the comparable imitation network considerably, and both networks outperform random chance by a mile. But we can look at this in a little bit more detail and look at a few examples. So here we see examples of the spatial selection accuracy. So on the very left, you see the ground truth. So these are the actual selections that were made by the human in the data set. We have the predictions made by the imitation network and the predictions made by our DSN. And generally speaking, what we see is that there is some alignment across all 3, but our DSN really dials them in and gets very close to the ground truth, whereas the imitation network tends to be a bit off, for instance, especially with node positioning. Likewise, we can look at the eventual final action selection, which shows similar trends. Here, the imitation network tends to do a little bit better, but we still get some wonky departures in terms of the actions selected when we compare to ground truth. So big takeaways from this work. The DSN framework can predict human decision-making behavior in complex action spaces like design. It does this by taking a hierarchical approach. So we start with identifying a spatial region and then identifying a distribution over likely actions. But more generally, DSNs can represent design behavior in complex action spaces, not necessarily just human behavior. So we want to make the case that DSNs can serve as a component technology in next generation design algorithms. Essentially, whenever you need to make a choice of what action to do next, DSNs are a good way to go. And we actually have a demonstration of how these can be used coming up at IDETC in a couple of weeks. So in this work, we used DSNs to enable a self-learning design agent that does tree search through a design space to design both truss structures and integrated circuit structures. So if you're at IDETC, I encourage you to come see our paper. With that, I'd like to acknowledge my co-authors, Ayush Raina and John Kagan, one more time, as well as our funding agency, DARPA. And I'd like to thank you all for listening to the presentation. Thanks.
Great. Thank you so much, Chris. Very much appreciated. Okay. So as a reminder, you can post questions in the chat and we'll get to it at the very end when we have everybody come together. Okay. Our next speaker is going to be Dr. Kshitij. He's a postdoctoral research associate at the Center for Integrated Systems in Aerospace at Purdue University. He obtained his PhD and master's from the School of Aeronautics and Astronautics at Purdue University and was a postdoctoral fellow in Aerospace University and Aerospace Engineering in Auburn University in 2019. And previously, he completed his BTech in Mechanical Engineering at the JSSATE Noida in India, and then worked for a year at Infosys Technologies as a computer systems engineer. And his research interests lie in the areas of optimal control theory, atmospheric flight mechanics, and explainable AI and human-class Mars missions. He'll be presenting his paper with a variety of authors. I won't list all of the names, but you can see the link to the paper in the chat, which is on mission engineering and design using real-time strategy games and explainable AI approach. So go ahead, Dr. Mall, whenever you're ready.
Yeah, namaste and good afternoon to all. Thank you, Mark, for a very kind introduction. And in the next 30 minutes or so, I'm going to share with you what my team has done in 13 pages. So there is a lot of information, but what the intent here is to share high-level detail of the work that we have done. We have, as you can see, submitted to Journal of Mechanical Design and luckily got accepted for that. The title of the paper has been Mission Engineering and Design Using Real-Time Strategy Games and Explainable AI Approach. Now you see a long list of authors, some whom like me enjoy playing games for a living, but on a serious note, actually it's not moving, just a moment, yeah. Our team has been looking at the mission design problem. And what happens in that is that we try to identify or pick those missions or engagements that helps us to maximize certain objective. For example, a probability to win a contest. And in this mission design problem or mission engineering and design challenge, one thing is that it involves a large and complex design spaces with evolving and dynamic mission environments. So that makes it extremely challenging in order to solve these problems. So there are a lot of simulation environments that have been built in order to address the challenges posed by mission engineering and design, M.I.T. Some of those are ASME, which is Advanced Framework for Simulation and Integration and Mission Software. So that is ASME for you. Then there is Command, Flashpoint campaigns, and whatnot. But these are actually very complicated simulation tools that are available. And some of those have been used by US Air Force, Department of Defense, DARPA, and such. But this project that was given to us was by DARPA called the Game Breaker program. And what our team came up with is learning to game break methodology, which is what we have devised and which I'm going to present on the same. And in that, what we looked at is these RTS games or real-time strategy games, which many of us enjoy playing for leisure. But here we have been using that in order to understand the dynamics of the game and how to use that and take it out to the real world. So how these RTS games help us is that they abstract or show a mission execution as a game played between different agents which have competing objectives. So like I said, we came up with this methodology or a framework where we have these different layers and different tools comprising artificial intelligence, explainable AI, Monte Carlo dropout networks for uncertainty quantification and whatnot. So there are a lot of complex things that are in that, which I'm going to share in subsequent slides. In that, one key thing that we used, or a concept called game balance, and what we defined balance is, like, a game is balanced when all the players that are involved in the game, they have equal chance of winning that contest or that game, given an environment for the game. Like whatever environment we have for the game, given that environment, if everyone has a same chance for winning that contest. One thing that we took out of this definition is the skill factor, which is the ability of a player to select certain strategy or certain sequence of events. So we took that out because it was getting more complicated, and our sponsor didn't want to include the skill factor. They just wanted to see, just based on an environment, how does it play out and what the game balance is. So the framework that we eventually devised is very efficient for mission design because it's able to build a surrogate model for the mission environment, which I'll be showcasing shortly. So this is the 3-layered approach that we came up with, and our team devised this having 3 different layers. One is the player layer, then there is a tournament layer, and then there is a game breaker layer. So all these layers, they talk to each other, and there is a lot of exchange of information. The player layer, actually, as you can see, there are self-play games. So in order to get the skill factor out, what we started doing is we have a bot player, and that bot player plays against itself. So that's a self-play game. So we started using that so that we don't have any skill involved, only the game environment. And you can see there are certain types of bots that we used. Some of them are deterministic in nature, which means they have a set strategy. They are not going to change it if we play it more and more times. But there are certain which actually change their strategy based on the different runs. So one of them is the portfolio AI, which we have used in this study for more complex results and for more interesting results. Now, when we have these players, we make them play different tournaments of games. And for that, we use something called design of experiments. And with that, we have a whole tournament set, which generates huge amount of data. That all data goes into and feeds into this game breaker layer. And there we have all these, like, artificial intelligent models, which are able to predict who is going to win the game. Is it player 0 or player 1 in our case? And then once we have these predictions, we want to make sense of those predictions. Like, why is player 0 winning and not player 1 winning? Is because there is certain thing going on in the environment or with the players. So for that, we use the tool explainable AI, and we use a particular tool called SHAP for that. And once we have these Shapley values or the results, then we are able to gain more sense of these predictions. And based on that, we are able to close the design loop, and we are able to guide the design of experiments again to run, like, what is more important and what the design space should be explored and we should focus more on. So those kind of things, this whole setup is able to address. Now, this is the game that we chose, and why we chose this micro RTS game is because it is one of the easiest games to understand. And what we wanted to show is that there is this 3-layered framework, and then it works. So in order to showcase some results in an easy manner to the community, we thought of choosing this simplest game, which is built for AI research. And then, just like any other RTS games, it has like 2 players with the light unit, heavy unit, and there are range units which are not used in our study. There are workers, resources, barrack spaces. So it is very similar to any of the games that we play, in which there is an objective of, you want to win, you have more units, you want to damage the other units of the player, you want to build more resources over time, and the one who has more point at the end of the game wins. So that is the objective of this game. And then this is a slightly like the snapshot or a zoomed in version of the 2 other layers, which is the tournament layer and the game breaker layer, and how they talk to each other. So like I mentioned, that we have these tournaments between different, like the player who is playing against itself. We have a lot of these different games for different settings. For that, we use design of experiments. And then we have these like 2 different types of data. One is like the image snapshot of the game, and then also scalar things like number of units of the players, the health of the units and all that. And then we use all that information in order to train a very complicated convolutional neural network, here in this case, along with dense branches, because we have two different types of data. And then once we have that model trained, we get the predictions out of that, and we are able to get a good enough accuracy for our model. So once we have that information, we also pass that information through the explainable AI model, which tells us that we have the sanity check through that. Is our model behaving correctly? And if it is behaving correctly, why is one player performing better than the other? Or why are both players like in a balanced situation? So those kind of things we are able to unfold and understand. And then you can see a lot of these feedback loops coming in, because they inform each other and tell that like, okay, these are the features that are important. We need to focus on these, and we need to change our settings so that we can build our model even better. Like the accuracy can go higher if we can do that. So that is the snapshot of the game breaker layer and the tournament layer and how they talk to each other. One other thing that I want the audience to take away from this is that this is a very generic framework. So what I'm presenting here is for a very simple game, micro RTS, but in reality, we have used the same concept and tried to solve a much more challenging game environment called StarCraft 2. Some of you might have played it. That is way more complicated than this micro RTS, and involves like very complicated bots and a lot of more features, and the design space is extremely complicated. But still, using the same framework, we just made some small changes, and we were able to tailor it for more complicated RTS games. And the same concept can be used for other domains as well. So that's the beauty of this framework, is that it's very generic. And like I shared here, convolutional neural network or SHAP, you can always go around and change these things based on your needs. So that is another good thing about this framework. And then I've been talking about the design of experiments. So in that, we have different attributes for either the player or for the game environment that I've been talking about. So those things you are able to change. They have certain values like a minimum or a maximum. Here, for example, the player I have fixed, so there is no minimum or maximum. But for certain other things, there are some ranges. So you can go and change around those things. We have used something called Latin hypercube sampling, which is a smarter way to use these, the values and to set up these tournaments instead of going the n factorial way and making like changing every single thing. So that we have used successfully. And we have 5,000 games that we generated using this design of experiments. And each game we played around 5 times, because we used a portfolio AI bot, which is more stochastic in nature. So total of 25,000 input games we had. And at the bottom, you will see some of the other features that have been used. One is the terrain feature that we introduced, so that there are some blocks or there are some challenges for the player to move around and its units to move around. And there is a certain region where the player 0 or the player 1 can spawn. So that is this 5x5 block. This map has been used as 16x16 because it had good enough space to traverse and to give us complex and interesting enough results. So that is why we have used this. And here is something about our model. The inputs that are generated using the tournament layer. What we have done is we had those 25,000 games, and for each of the games, we captured 30 game frames, because otherwise there are just tons of them. So we had to reduce the size so that it's computationally feasible to train this model. And then we had 2 different types of data coming in. Like I said, there is a spatial data or a geographic data, and there is a non-geographic data. Both of them feed into the model. And then out of that, we get certain game balance metric, which is useful for us. So here we have chosen something very simple, is which player is going to win? Is it player 0 or player 1? So that probability it tells. So that is in short the model that we have used. And this is a more detailed snapshot of the model that we have generated. You can see there are tons of blocks here, and there are all types of layers, because we have different types of data used. So we had to use different types of layers, one to address the image data and other to address the non-spatial data. And then we concatenated them and merged them together in order to finally have the predictions out. So one other good thing is you can see we use something called Monte Carlo dropout method which helps us to make the model less sensitive to the inputs, because what it does is it keeps changing the connections between the neurons. It switches it on and off. So there is some uncertainty involved. And that's why we are able to see if the model is more sensitive to certain inputs and if it is not. So we using this, we are able to gain sense of what time the model is able to predict more accurately or more with more confidence, and at what times it is not. And there are certain times in the game where it is expected that the model should not be able to predict with high certainty, because even we don't know what's going on. Only when the game passes to a more advanced stage, we come to know like, okay, player 0 is going to definitely win, or player 1 is going to definitely win, or it's going to be neither, like it's going to be a draw. This is one of the very cool things that we used, and primarily I've been assigned this task of getting SHAP into play. This is one of the explainable AI tools, which is very popular nowadays. It merges around 7 different explanation methods that are out there. And the objective has been to, like for different types of AI models, we can just use the SHAP tool and we are able to explain the predictions, like why certain things are happening. And since you know that we are using games, and these games involve either player features or environment features, so we care about the importance of these features, like which feature is more important and what we need to pay more attention to. So if you see, we usually have some training data that feeds into a CNN model, and then we get some prediction. But what the SHAP does is it maps this training data into either the feature is contributing to something, some useful output, or it is not. So it's between 0 and 1. And then that information goes into the explanation model. And what we get out of that is Shapley value. So these Shapley values, they actually tell that what is the contribution of a particular feature. Is it actually adding to the win of a player, or is it actually taking away from the win of a player? For example, if the health of a player is very good, that is actually helping it to win the situation. If the player has more number of units, it's going to help the player to win the situation. So things like that, this is able to uncover through the Shapley values. Another thing that the SHAP does is it tells us whether your model is correct or not at the first place. If you are getting very random answers, that means more likely or not, your model itself is incorrect. So in our case, our model turned out to be good enough, but then we were able to uncover some very interesting scenarios out of it. Also, it helps in something called optimal learning, which we have not been able to implement in this study. But the idea is to, smartly explore the design space in an optimal way, instead of, searching the whole big design space and investing a lot of computational resources on the same. Moving on to the results, some of the interesting results that we found is the very first one actually started our team because we posed a game situation in which everything was kept symmetric. A player is playing against itself. That means both the players are same. Everything else, like the number of units, the resources, the situation, the position, the location, everything is the same. Even then, we saw that there is an initial imbalance in the scenario. And then we thought, like, why would that be the case? Then we found out that even if you keep everything the same, there is an inherent imbalance. This is because of the movement order and the path planning logic implementation, because at certain time there may be conflict, and then in order to resolve that, one player will be given an advantage over the other. So that has to be resolved. We cannot keep sitting there and then both players are in a stalemate situation. So the designers have designed that in that way. And our team actually got in touch with the maker of the game, Professor Antonon, and he also agreed that movement order is actually the reason for this imbalance, and path planning falls prey to that. This is another interesting result you see, like for one of the games that we had. And this was again given to us by our sponsors, DARPA. So here what you see is written perturbation 1, which is one of the perturbations they gave to us. And in this, what you see is that this game is highly balanced at the start. Like this is the prediction. It's basically 0.5 for a long time. And then one of the players start winning and the other starts losing. So for this particular game, we said like, okay, things are balanced. And what we need is to identify some of the key game features. For example, the position, base location, the number of units, or the damage rate, or the health of these units. So those were identified as some of the main units. And you can also see the SHAP values here. One other thing I would like to tell is how we read these SHAP plots is that whatever is in red, that is contributing to the outcome. It is positively affecting the win of a player. And here it's the opposite. If it's a blue, that means it's taking away from the outcome. So you can see health of player 0 is negatively impacting and health of player 1 is positively impacting the situation at this particular game frame, which is the first game frame. So for this, what we did is we identify the game features which are most important, and then we altered them a bit. And we tried to see like, okay, if we change certain things about this game, and we know intuitively like, okay, if we decrease the health of the player, then it should start losing the game. And this is what you start seeing, like player 0 starts losing the game, player 1 starts winning the game. Before that, it was actually like a mixed contest. But as soon as we made this change, things will start happening a different way. So here the predictions align with whatever is observed. Similarly, when we increase the damage rate that a player can do, it starts actually winning the contest. Player 0 starts winning the contest here. But the third thing that we try to do is we changed the location of player 0 to a different location, which we thought is more favorable for player 0. But then the model actually predicted in a counterintuitive manner. That is because some of the things our team also did not understand very well is like when we change the position, there is also a relative change in the location of the resources. And there is also a change in the relative location with the other player. So there is a lot of like this complicated coupling of, a lot of other things that is going on, which we were not able to capture in our model. And that requires us to feed more training data and such. So that was the interesting thing that we found out with these 3 perturbations.
Dr.
And
Mal,
you can see,
could you please conclude your talk soon so that we can move on to the other speakers? Thank you.
Yeah, sure thing. Thank you. So basically what I have to tell on this slide is that you can see these SHAP values, they seem to be similar, but at the end, there is a small change or there is a small differential because of which you can see one player winning and the other player not. So it is that small change in the SHAP values, which is important to be noted on this slide. And then we just have to design our experiments based on all these features. And we need to pay more attention to these things which the SHAP has uncovered. So that helps us in closing the design loop. And at the end, the key takeaways from this are that we saw an initial imbalance, and whenever you are designing a game, you should pay attention to this initial imbalance, because even if you think everything is balanced, it may not be the case. Secondly, our team came up with a very generalizable and scalable methodology that includes CNN and SHAP and things like that, which predicts and explains the game balance for any game state and efficiently enables us to navigate through the large design space, which is one of the challenges for the mission engineering and design domain. And then we were able to incorporate uncertainty quantification and able to close the loop by identifying some of these relevant features. So thank you so much for your time. And thanks, Mark, for helping conduct this session. Thank you.
Thank you. Okay. As a reminder, you can place any questions for the speaker in the chat. Okay. All right, so now we'll move on to our last speaker for today, and that's Dr. Caitlin Mueller. She's at the Massachusetts Institute of Technology and is a researcher, designer, and educator working at the interface of architecture and structure engineering. She's currently an assistant professor in the Building Technology program, where she leads the Digital Structures Research Group and co-directs the Structural Design Lab. And her research focuses on developing new computational methods and tools for synthesizing architectural and structural intentions in early stage design, and also works in the field of digital fabrication with a focus on linking high structural performance with new methods of architectural making. In addition to her digital work, she conducts research on the nature of collaboration between architects and engineers from a historical perspective, and also aims for interdisciplinary learning and integration in her teaching efforts, which includes subjects in structural design and computational methods. And then for the question, she'll be joined by her co-author, Dr. Eamon Whalen, who's an engineering data scientist at Altair, and his focus is on how machine learning methods are disrupting the way we design, build, and test products. And before working at Altair, he earned his bachelor's in mechanical engineering from the University of Michigan and a master's in computational science from MIT. Dr. Mueller, take it away.
Great, thank you, Mark, and thanks for organizing this very interesting session. So our paper is entitled Towards Reusable Surrogate Models, Graph-Based Transfer Learning on Trusses. And I come from a slightly different background than most of you. I'm based in architecture and structural engineering. And in my work, I'm really interested in understanding representations for design and interactions between geometry and performance. And this is an example of a design space that I work with a lot, where we have a kind of a continuous parameterization of a truss structure. And what's interesting about the design space is that in addition to the optimal solutions shown in the middle, we have a lot of other high-performing solutions that might be more relevant for applications in architecture, building structures, or bridges. That's because a lot of design is not just about optimization in my world, but is really about balancing the qualitative and quantitative goals that make creative design processes so interesting and challenging. In particular for trusses, I think it's important to note that geometry and topology play a huge role in both the aesthetics and how a truss looks and whether it's acceptable for an architectural application, and also how much material it requires, how stiff it is, what its environmental performance is. And so I'm interested in developing approaches to help not only engineers, but also architects understand this relationship and leverage it in a creative way in early stage design. One of the ways that we try to do that in my group is with surrogate modeling. Our motivation is really both speed and portability. So for creative design, having interactive tools that don't have to slow down for simulation is really critical and really allows designers to stay in this mode of flow where they can maximize their creative output. And surrogate modeling is a really old idea, as all of you know, where we basically do supervised learning on a small discrete set of simulated data and build a predictive model that predicts unseen data points in the design space using some kind of regression technique. And this approach has been widely applied in many fields, but in my area in buildings, it's rarely used so far today. I think one of the challenges is because the ways that we learn on surrogate models, the features that we learn on are not necessarily flexible enough for the types of design problems that we have, and I'll show you why in a second. So here's one example of surrogate modeling for a building structure. This is a shell structure, maybe made out of thin shell concrete that resists loads mainly, but not entirely through membrane action. And what we see here is a surrogate model that predicts displacement in X, Y, and Z as a designer is interacting with it. In contrast to a traditional engineering technique where the designer comes up with a geometry and then an engineer simulates it, this is much more interactive and engaging and allows a designer to really be creative with form while understanding performance simultaneously. So I think surrogate models are really powerful as a way to bring simulation into design, but they're also fairly rigid and non-generalizable. So what do I mean by that? A surrogate model usually learns on some kind of features, and traditionally these are hand-coded or manually coded parametric features that encode a design, and then we can learn a response based on the values of those features. So that works really well for kind of continuous morphing of fairly narrow sets of ideas. But if we want to explore a wider design space, it's very difficult to understand what kind of surrogate model we should build because there's no hand-coded features that can apply to all of these diverse designs. So as soon as we leave the original design space, we can no longer use the surrogate model on new unseen designs. And we're also very inefficient with data. We basically need to generate a brand new data set every time we want to leave one parametric design space and go into another. So our work addresses these challenges. One of the opportunities that a lot of us have noticed in recent years is that new advances in deep learning, and in particular, geometric deep learning, offer opportunities for us to decouple surrogate modeling from manual parameterization as the features that we learn on. And so there are a number of different geometric representations for designs that are compelling that people have studied. Image-based or pixel-based are especially popular because of the prevalence of convolutional neural networks, but people have also tried learning on point clouds or on meshes or graphs, which I'll focus on today. Previous work has identified these opportunities to learn a performance response not from hand-coded parametric features, but instead from some kind of geometric representation of a design or topological representation of a design. And in particular, because this paper is about trusses, we found that the image-based approaches, while useful in certain applications, are really not very high fidelity for trusses, whereas graphs, trusses literally are graphs. And so trusses or bar-based structures are really good candidates to try graph-based learning representations. And on the right is one previous paper that also uses this approach. Our paper is different in that we really focus on geometric variation in the design space. So what are graph convolutional neural networks? If you know about regular convolutional neural networks that operate on bitmaps or images, they have a similar approach where data is convolved over in order to understand relationships of points in the design representation and the neighboring region, the benefit of graph convolutional neural networks over regular CNNs is that they don't require fixed length vector input for the representation. We can learn on graphs of varying topologies, which is really valuable for what we're trying to do in our process. So we're using the method that's shown on the right, which is a previous paper published by other people in 2018 called FeastNet. And we built a neural network using FeastNet to predict the responses of truss structures of varying geometries and topologies. We call this approach graph-based surrogate models, or GSMs. And the idea is you input the truss as both the topology of the graph, so the list of the connectivity of all of the edges to all of the vertices, and then each vertex is encoded with both its location in space, its coordinates, that's the C in this input over here, and also the boundary conditions. So this supports whether each node is fixed in either of the boundary conditions and whether it's loaded in either of the boundary conditions. And those are the inputs, and the outputs is another graph that predicts the displacement field in X and Y in this case for all of the nodes of the structure. And the key really is this FeastNet convolution, which again applies a convolution to neighboring to a node and its neighbors to consolidate information about, to try to learn patterns of how loads are being transferred basically, or how displacements are occurring within this truss network. And because of the flexibility on topology of the graph-based surrogate model, we also applied another existing technique of transfer learning, where we can build a graph-based surrogate model with one set of data and then use transfer learning to adjust it to another very, very small set of data and to get pretty good results, which I will show soon. In order to test this approach, we devised a large synthetic data set using parametric models of trusses of varying geometry and topology. This is one of the parametric models that varies just in geometry. And then we had multiple parametric models that we built these GSMs over. So here's a kind of overview of all of the synthetic data that we used. The first 5 rows, DM5 through DM9, are all bridge-like trusses supporting continuous loads, where the only difference between them is the number of subdivisions, or essentially a small change in topology. We thought that was kind of a modest request to study generalizability for our network. We then also studied more diverse design spaces. So we also included a change in loading, so the same structure as DM8, but then loaded only on its ends. And then we also tried fairly different structures like a tower and a bridge. And the goal is to see whether the GSM can be trained on only a subset of this data and then apply well to other data. In order to test that hypothesis, we devised a list of experiments or basically trials that we trained different versions of the model on different data sets, and then we tested it on other data sets. And this is basically going in order from sort of the easiest task to the hardest. The first task is not studying generalizability, it's just studying whether the GSM works at all. So I'll show that result first. So here is an overview of test data for the GSM versus what we call a naive alternative, a pointwise surrogate. This is just a normal MLP model that individually, there's an individual MLP model for every node that every degree of freedom and every node that individually predicts displacement. And we think that's a reasonable baseline comparison. The huge downside of the pointwise surrogate is that it's not flexible on topology. So our GSM is much more flexible. And we see here that we get very good results, similarly good results to the pointwise surrogate with the GSM, with the added benefit of the flexibility. If we look at the more challenging cases where we try to test the model on data that it was not trained on, which represent these other cases, we'll see varying results of varying success. So here's one example of a result here. This is one of the easier problems where we trained the model on 4 of these truss bridge parametric model data sets, and then we tested it on a slightly different one with slightly different topology. And what this graph shows is the mean absolute error of the test data in centimeters. And remember, this bridge is spanning, I think, something like 10 meters. So all of these are pretty good. And N is the number of training samples used. The The dashed line here represents another kind of baseline comparison of a predictive model that just predicts the mean of the training data. So that's a very bad model. So anything we expect to be good should be way better than that. And the boxes here are the pointwise regressors, the alternative that I described earlier. What we see is for very small numbers of training data, the GSM actually does very poorly, but as the amount of training data increases, it does better, but it never does quite as well as the pointwise regressor, at least not in terms of MAE. When we do transfer learning, however, we are able to get better data than what we see with better results than what we see with the GSM. And I'll say more about that in a moment. I won't discuss all of these other scenarios because they're all represented in the paper, but basically, in general, we see the same trend where the transfer learning improves the behavior of the GSM substantially when compared to both the baseline model and the pointwise regressor. For some of the more challenging cases, like here where we're learning on the tower or learning on the bridge, basically where the test problem is very, very different than the training data, expectedly we see worse performance, although still significantly better performance, at least in the last case, than the baseline. We can also study generalizability more specifically by looking at some of the test results. So here is just one of these cases examined in more detail, where we're looking at a histogram of the MAE for the GSM with pre-training versus without. And what we see here is that the transfer learning and the pre-training really makes this method quite viable. We see that we are able to learn on unseen data of different topology than the training set with very good accuracy, with only a small amount of additional data needed. The amount of additional data that we need is also something that I'll show in a second. So let's look at this other case. This is one of the hardest problems where we train on a bridge and try to predict the behavior of a tower. What we see here is that as we increase the amount of data that we have for the new data set for the tower, if we don't have pre-training, we're better. So the first row at the top is showing a kind of a not very good result for a non-pre-trained GSM, where we're just directly applying the bridge model to the truss model. But the blue histograms represent the behavior when we do use this pre-training or we do use this transfer learning. And what we see is that the behavior is both quite good and also quite stable, even with a very small amount of additional training data. So this suggests that we can generalize surrogate models to fairly diverse unseen data, even with just a small injection of additional data if we use this pre-training and transfer learning technique. So to conclude, we think these graph surrogate models are a promising direction towards more generalizable approaches for simulating or predicting structural behavior with surrogate models. We think they're more flexible than these rigid traditional surrogate models because they don't require a dependency on hand-coded parameterization. And the transfer learning works really well with GSMs because they have flexible topology. It's really easy to combine it and it can achieve excellent data efficiency. We'd like to expand this approach to more diverse data sets beyond the kind of the synthetic data that we use to characterize the approach in this paper. So we're really interested, for example, in wild data that comes not from synthetic computer experiments, but from real design competitions or design examples from the wild. So we'd like to try that in the future. And we'd also like to confirm that this approach is also relevant for more complex structural responses. This paper, we just showed linear elastic results because it was more about the method and not necessarily the structural behavior, but obviously surrogate models have more value for more complex and slow simulations. So we'd like to confirm that that will still work. And with that, I'd like to thank you for your time and looking forward to the discussion. Thanks very much.
Great, thank you, Dr. Mellon. Okay, so that concludes the 4 main talks that we have for today. Now what we're going to do is we're going to move into question and answers for the speakers about their individual talks, and then we can also have some wider ranging questions about the commonalities between the talks. So what I might recommend is we actually had quite a few questions that came in through the chat. So what I can do is I'll ask people if they would like to ask their question again, they can. If they don't respond, then I can ask them on their behalf. And we can just go in order of the ones that were listed in the chat. And then